Today's topic is diffusion models for image generation. In the next few minutes, I'll show how a single sentence can turn into a studio-ready picture, how we can tweak images by just describing the change, and where this is already saving time, from concept art and product mock-ups to marketing visuals. I'll keep it practical. One quick demo, how diffusion model learns and how a text turn into an image. I'll also flag the limits and the ethics we should keep in mind. By the end, you'll know when to reach for diffusion, and how to make it work for you. First, we'll look at how diffusion models learn. We'll see how they start with random noise and gradually learn to denoise images through training, capturing the underlying patterns of real visuals. Next, we'll move to text-to-image generation, how a simple text prompt, like a sunset over the mountains, can be transformed into a vivid, realistic image using deep learning and latent diffusion techniques. Finally, we'll discuss applications, from creative design and advertising, to game development, healthcare imaging, and more, where diffusion models are revolutionizing how industries create visual content. So, let's dive in and uncover the magic behind these intelligent image creators. So, what exactly is a diffusion model? Imagine you drop a bit of ink into a beaker of water. At first, the ink is concentrated, but gradually, it spreads out, or diffuses, until the color is evenly mixed. This is a natural process where order turns into randomness. Now, diffusion models take this everyday idea and flip it. In machine learning, a diffusion model starts with an image and gradually adds random noise until it becomes pure static, like losing all the structure. Then, it learns how to reverse that process. If we can train the model to undo the diffusion, to go from noise back to a clear image, it can generate new, realistic pictures from nothing but random noise. So, in essence, a diffusion model learns how to reverse chaos into creation. And that's the foundation of how today's AI image generators, like Stable Diffusion, can create stunning images from simple text prompts. First, the big idea. Diffusion has two halves, forward diffusion and backward diffusion. Forward diffusion is the easy, fixed process. We take a normal image and, step by step, add tiny bits of noise. After enough steps, the image becomes pure, indistinguishable noise. Backward diffusion is the learned process. Starting from that random noise, the model removes noise a little at a time, steering the pixels back toward a clean image. Now, let me anchor this to what you see on the slide. To the top, there's a strip labeled Fixed Forward Diffusion Process. Watch how a clear picture gradually gets speckled, then grainy, then totally noisy. That's forward diffusion, predictable, the same every time. To my right, you can see a panel that begins with an image and shows it being corrupted step after step. Think of it like turning up the static on an old TV a tiny bit with every tick of a clock. To my left, you see the reverse. We start from pure noise. Over many small iterations, the model predicts and subtracts just the right amount of noise. Shapes appear, edges sharpen, and a recognizable scene emerges. That's backward diffusion, the part the model learns during training. Why does this work so well? Because adding noise is simple and mathematically controlled, the model only has to learn the precise undo move for each step. Chain those tiny, accurate corrections together, and a believable image materializes from randomness. So, diffusion is a two-act play: corrupt in the forward direction, restore in the backward direction. Start with noise, apply the learned denoising steps, and you end with a clear, compelling image.
Hi everyone. In this part, we will dissect the training process step by step to understand how these models are built from the ground up. The entire generative process is guided by a text prompt. For the model to understand this prompt, it must first be converted into a meaningful numerical representation. This is achieved using a pre-trained text encoder such as CLIP. The prompt is first deconstructed into tokens. Each token is then mapped to a high-dimensional vector, known as an embedding. These embeddings don't just represent words, they capture semantic meaning and relationships, forming the conceptual blueprint that will guide the image generation. The foundation of training is the forward diffusion process. For the model to learn how to remove noise, we first have to show it what noisy images look like. We start with a clean image from our training data. In a series of steps, we gradually add a small amount of Gaussian noise. The amount of noise added at each step is controlled by a noise schedule. We repeat this process hundreds or even 1,000 times until the original image is completely transformed into pure random noise. It's important to remember that this forward process involves no learning at all. It's a simple, deterministic mathematical process designed to create the noisy training data our model will learn from. This brings us to the reverse process, which is where the model's actual learning happens. We give the model a noisy image from any step in the forward process and ask it to do one thing: predict the noise that was added to create that image. It's not trying to predict the final clean image directly, just the noise component. For this task, we use a specialized neural network architecture called a U-Net. It works in 3 stages. First, the encoder takes the noisy image and compresses it, capturing its essential features. The bottleneck in the middle understands the most abstract high-level details. Finally, the decoder works to reconstruct the image, but now with the predicted noise removed. The secret weapon is skip connections, which bridge the encoder and decoder, allowing fine-grained details from the early stages to be reused, ensuring the final images are sharp and not blurry. So, how does the U-Net know what to denoise the image into? It can't just be random. This is where our text embeddings come back into play, through a mechanism called cross-attention. At each stage of the denoising process, the U-Net is allowed to look at the text embeddings. Special cross-attention layers inside the U-Net align the visual features it's working on with the meaning from the words. So, the U-Net receives 3 key inputs: the noisy image, the current time step so it knows how much noise to expect, and the text embeddings to guide it. This is how the text prompt guides the denoising process from pure noise into a coherent picture. Finally, how does the model get good at predicting the noise? It learns from its mistakes using a loss function. For each training example, the model predicts the noise. We then compare that prediction to the actual noise that was originally added, using a simple formula like mean squared error. If the prediction is far off, the error is large. This error signal is then sent backward through the entire U-Net using backpropagation. An optimizer, like the popular Atom optimizer, then makes tiny adjustments to the millions of parameters in the U-Net to reduce that error for the next time. This cycle of predicting noise, calculating error, and updating weights is repeated millions of times with millions of images. Over time, the U-Net becomes an incredibly skilled expert at removing noise in a way that is guided by text. It's important to realize the model never memorizes images. It learns the underlying patterns and the process of reversing noise, which allows it to generate completely new images it has never seen before. Now that we understand the concept, let's see how to actually build this in Python. In this short walkthrough, I'll explain how to train a diffusion model to generate 32 by 32 images from the CIFAR-10 dataset. We'll see the data setup, the U-Net model, the noise schedulers, the training loop, and how we sample new images. This is a small demo model trained for few epochs to keep it fast, so the sample images you'll see are intentionally rough. First, we import libraries: PyTorch and TorchVision for training and data, Matplotlib for plots, and diffusers for the U-Net model and schedulers. We also detect the device, CPU or GPU. Next, we set a random seed and define our configuration. Things like image size, batch size, learning rate, and number of epochs. Simple helper functions also appear here. For example, denorm converts tensors from the training range back to regular images for viewing. We prepare CIFAR-10 with 2 transforms, one for showing raw images and one for training that normalizes data to the range -1, 1, and adds a light horizontal flip. A data loader feeds mini batches during training. The code displays a sample batch of CIFAR-10 images so we can visualize what the dataset actually looks like. The model is a U-Net tuned for 32 by 32 inputs with attention blocks for better quality. We also create a DDPM noise scheduler. It defines how much noise is added at each time step during training and how we remove it during sampling. Here's the heart of training. For each batch, we pick a random time step, add the corresponding noise to the real image, and ask the model to predict that noise. The loss is mean squared error between predicted and true noise. We use AtomW for optimization, cosine learning rate with warm-up for smooth training, automatic mixed precision for speed on GPU, gradient clipping for stability, and an EMA, exponential moving average, that keeps a smooth copy of the weights for cleaner samples. To build intuition, we visualize forward diffusion, starting from real images and adding noise at different points in the schedule. By the end, images look like pure static. Reverse diffusion goes the other way. We start from random noise and repeatedly denoise using our model and the scheduler's steps. This sequence shows the image forming over time. For final samples, we use the EMA weights. DDPM takes many steps and gives top quality. DDIM is faster, fewer steps, and can still look great. The code provides a simple function to run either scheduler and display a grid. These grids look rough because we trained a tiny model for only a short time. That's by design to keep the demo quick. In practice, you'd train longer and/or use a larger UNet and more sampling steps for noticeably better images. Finally, we save example grids to disk so you can compare methods or track progress between runs. And that's the full pipeline. Prepare data, build the UNet and scheduler, train by predicting noise, and sample new images. Try training longer and always sample with EMA for best results. Alright, now I will explain how a text prompt becomes an image through diffusion models. First, in step 1, the model needs some basic inputs. The prompt itself, a negative prompt to tell what we don't want, CFG value, the number of steps, seed, and image size. These act like the foundation and settings for the generation. Usually we give the prompt a negative prompt and the diffusion model decides what the other values are. In step 2, the text is broken down into tokens and converted into numerical embeddings. This means the model can actually understand the meaning of our words. Since Ruvindu explained this earlier, I'll just add that this step is like translating our language into a format that the AI can use. Then, step 3 introduces random noise. This initial latent noise is generated by the seed itself. And step 4 is where the sampler gradually removes that noise step by step, shaping the image. Think of it as cleaning a foggy picture until it becomes clear. In step 5, the UNet with cross-attention is used. UNet compresses and then expands the image to understand the overall structure and recover details. And in step 6, cross-attention links the noisy image parts with the words in the prompt so that the image actually follows our description. I won't go deep here since it was explained before, but simply this is how the text and image align. Next, in step 7, the model makes 2 predictions of the image, one without the prompt and one guided by the prompt. CFG Combine blends them. It's like turning a volume knob. Higher makes the image follow the text more, lower makes it look more natural. And finally, in step 8, the VAE decoder transforms the cleaned latent, which is the final noisy image, into the resulting image we see. VAE stands for Variational Autoencoder. Actually, the encoding part is used in IMG2 IMG generations. Here we use decoding. Here's the quick journey from prompt to pixels in 4 steps. Now, when we take an example like a cat wearing sunglasses on the beach. First, when you type that prompt, the model doesn't see words, it converts them into numbers, almost like a secret code. Second, the process begins with pure random noise, like static on an old TV screen. Third, the model removes that noise step by step while checking against the prompt's code. It's a bit like sculpting, starting rough and slowly shaping it to match the details. Finally, the cleaned up result is decoded into an actual image of pixels. That's the magic unpacked in simple steps. When we look at diffusion models in the real world, they aren't just fun tools that turn text into pictures. First, creative design. Artists and designers use them to brainstorm ideas quickly. Imagine being able to sketch 10 different logo concepts in seconds or explore new fashion styles without touching a pencil. Second, entertainment and media. Movies, animations, and even video games use diffusion models to generate storyboards or entire fantasy landscapes. Third, science and education. Researchers use diffusion to create realistic images of molecules, proteins, or even medical scans. This helps doctors train on simulated data when real patient data is limited. Fourth, personalization. Apps now let you generate custom avatars, edit selfies, or even imagine how your room would look with new furniture. Of course, these models aren't perfect. They raise questions about ethics, bias, and copyright. Learning to build a diffusion model is a lot like constructing a house. You need to build it step by step. Step 1, the foundation. This is Python, math, and data basics. Things like probability, stats, and linear algebra form the solid ground. Step 2, the frame. Here you learn machine learning and neural networks, the main structure. Step 3, the walls. These are generative models like autoencoders. They teach you how to add noise and then learn to remove it, almost like putting in the plumbing and wiring. Step 4, the roof. Now comes diffusion itself, learning how to start with pure noise and step by step remove it, guided by a prompt until an image appears. Step 5, the interior. Finally, you explore real tools like PyTorch or Hugging Face to run pre-trained models, fine-tune them, and even build your own mini app. This is like decorating and making the house livable. By following these steps, you don't just move into a ready-made house, you actually learn how to build one yourself. So, let's wrap up everything we've explored today. If today's talk leaves you with one takeaway, it's this: diffusion models are not magic. They are understandable, buildable, and open for you to explore. What we've given you is just the spark. The rest is up to your curiosity and where you choose to take it. Thank you.